Welcome everybody to another session from Neuro Research. I'm Srijit here, and in this video, I'm going to continue the applications of NEGF formalism with gate bias potentials. So, actually, like our previous videos, NEGF formalism is a powerful theoretical framework used to simulate electronic transport in nanoscale devices, particularly when quantum effects are significant. It's widely employed for studying devices like molecular junctions, nanowires, and transistors. When simulating such devices, applying gate and bias potentials are crucial for understanding their electrical characteristics. So here in this video, I'm going to brief you that how gate and bias potential are generally incorporated in NEGF through band engine. So speaking about gate potential, it is typically used to modulate the electronic properties of the central region of a device, similar to how a gate controls current in a transistor. So in NEGF, the gate potential modifies the electrostatic potential in the central region, which in turn affects the Hamiltonian of the system. So this is actually an example which I have taken to brief this concept. And speaking about electrostatic coupling, the gate interacts electrostatically with the channel. This interaction is usually described by solving the Poisson equation, which self-consistently with the NEGF equations. So the Poisson equation relates the charge density to the electrostatic potential. And speaking about the potential region, in this package or computational methodologies, we often define a specific potential region using the device setup where the gate potential is applied. So this region usually encompasses the channel and parts of the surrounding dielectric or gate electrode. Speaking about the self-consistency, the NEGF equations and Poisson equations are solved literally until a self-consistent solution is reached. This means that the electron density obtained from the NEGF calculation should produce the same electrostatic potential via the Poisson equation. And how we can effect or how we can brief the effect on band structure. So the gate potential effectively shifts the energy bands in the channel region, and also a positive gate voltage typically lowers the potential energy for electrons, bringing the conduction band closer to the Fermi level and increasing the electron density, or pushing the valence band further away. So this modulation of the energy bands directly influences the transmission function and consequently the current. So that's about gate potential. And now speaking about bias potential, it drives the current through the device by creating a differences in the electrochemical potentials of the left and right electrodes. So the chemical potential differences in NEGFs, the bias potential is implemented by setting different chemical potentials for the left and the right is the electrode. So the applied bias voltage is typically related to this difference. So this is actually the general introduction about gate and bias potentials. So how this thing can be implemented with, or how this can be briefed with the help of AMS band engine. So speaking about this aspect, so applying gate and bias potential is the core aspect for simulating electronic transport. So speaking about this AMS band, how we can introduce that thing. So the system is typically divided into three regions: the left lead, which is known as the source. So this is actually the left lead, and the central scatter region, the device where the transport happens. So this is actually the central transport region, and then the gate potential or the right lead, which is known as the drain. So the gate potential usually act on the central region while the bias is applied across the leads. And speaking about the self-consistent calculations for realistic simulations, especially with the bias and gate potentials, the NEGF calculation must be consistent with the electrostatic potential via Poisson equation. This means that the electron density calculated by NEGF influences the potential, and that the new potential that influences the NEGF calculation until convergence. And then how we can set up this calculation or this exact setup or the workflow. So let me show you in simple steps. Let me open a new input. So After opening up the new input, I will quickly dismiss. Okay, let me go to this band engine and then changing the task to NEGF, and then just making it self-consistent, and then opening up our first potential. So I have already downloaded it, and now we will set the tips as shown in the right and left. We will select the atom at the tip. So let's do it. Before adding that thing, sorry, let's fill the central region with 4 layers of the lead, and now just rearrange the lead left lead, so 0.85, and the right lead is positive 8.5 angstrom. And now we will upload this bias potential calculation. We need to set that coordinate file from files and then downloads. Just uploading that file. Yes. And now we will make it a little bit complex. We need to select the gate potential as well as the bias potential. So now we need to select and then the left. So this is actually the regions which we need to select accordingly. So this is the method, and then we will set the voltage to 0.1 for gate potential, and then bias potential we will change to 0.1, and then the X range ramp to -3 to +3. And before saving it, we need to check the inputs one more time, the NEGF, the properties, sorry, model, the regions, and NEGF. So I have already executed the calculation. So this is actually the input files which I have already set for this. So once we set all those inputs, the regions will be visualized like this, and I have already executed the calculation. So let me show you that output file. What was this? So I'm just showing you this output file of this calculation. So I'll be just opening this NEGF KF browser. So once I open the KF browser, it will be displaying a window like this. Just I need to select the file, related files, then band.rkf. Actually, we have used this band engine for this calculation, and then we will be looking at the NEGF section. So we will be going to file expert mode, and in this expert mode we will see the NEGF at the bottom, and from this NEGF we can see the current. So the current will be around minus 0.032 volt. So this is actually the expected result of this calculations. So I have taken this typical example from the tutorial itself. So I will show you what would be the expected output from the gate and bias potentials. So you can see after doing the calculation, so this could be the current, which is around minus 0.0321 volt. So this is actually the expected result from this calculation of gate and bias potentials. So I have briefed the same tutorial with that worked out example. So thank you for watching this video, and for your more information I would request you to kindly subscribe our channel and also follow our LinkedIn page. Thank you, and we will see you in the next video.